We've seen that an amount that grows at a constant percentage rate can be described with an exponential function, but that constant rate of percentage change can be negative, in which case the amount isn't growing, it's getting smaller. And we call this situation exponential decay. The actual model looks very similar. Q of t equals Q sub 0 times e to the RT, but we typically put a negative in front of R so that the parameter R still represents a positive amount, and that negative signals that we're talking about exponential decay. When we talk about exponential decay, instead of referring to doubling time, we can talk about things in terms of half-life. So let's take a look at what half-life represents. As with doubling time, it's going to be independent of Q sub naught, because half-life is calculated by setting our model equal to half of Q sub naught. And then to solve for t in terms of R, the first thing we want to do is divide by Q sub naught. So we end up with 1/2 equals e to the negative RT. And then of course we can take the natural log of both sides. And simplifying that expression gives me the natural log of 1/2 equals negative R times t. So t, the half-life, is equal to the natural log of 1/2 divided by negative R. But we can simplify this a little bit further because using the fact that 1/2 equals 2 to the negative power, and also using the power rule for exponents, I can rewrite the numerator as negative natural log of 2 divided by negative R. What we end up with as a half-life formula turns out to be exactly the same as our formula for doubling time. But let me acknowledge that we're taking R to be a positive value, and in our formula including a negative sign to indicate that we're talking about exponential decay. An important example of exponential decay is radioactive decay. Carbon-14 is a radioactive compound that occurs naturally in all living organisms. It's actually brought into our bodies by breathing. It exists in the atmosphere, but then when a creature, a plant, dies, it no longer interacts with the atmosphere and the carbon-14 starts to decay. So the amount that's left in a formerly living thing, an organic thing, can be used to date how old that thing is. Well, in this problem, we're given that the half-life of carbon-14 is 5,730 years, and we can use our half-life formula to figure out the value for R. The half-life formula is T equals the natural log of 2 divided by R. We know that half-life in this situation for carbon-14 is 5,730 years. So we can plug that in for T and then solve for R. Multiplying by R and dividing by 5,730 gives us the half-life. Of course, we can use a calculator to get something that's a little bit more workable. Plugging this into a TI-84, you might see something that looks a little bit like this with an e to the negative 4 at the end. Remember that that represents scientific notation. So what we really have is 0.000121-ish approximately as our value for R. So I can use that to build my formula. Again, in general, Q of t equals Q sub naught e to the negative RT, and we just found a value for R. We don't have a value for Q sub naught. We're not given that in this problem, but we actually don't need it because what we know is that the wood has 60% of the normal amount of carbon, and so that's relative to what's usually there. That's relative to our initial value, and so we can write this as 0.6 times Q sub naught and set that equal to Q sub naught e to the negative 0.000121 t. Of course, we can solve this because our first step is going to be to divide by Q sub naught, and we end up with 0.6 equals e to this power. And next we can take the natural log of both sides to get the natural log of 0.6 equals negative 0.000121 t, and t equals natural log of 0.6, which is going to be a negative value divided by negative 0.000121. And if you type that carefully into a calculator, you should see that the age of this piece of wood is 4,221.7 years. So I just want to end this video with a comment about accuracy. We definitely did some rounding in our process for finding the age. When we took the half-life to find the rate of decay, we rounded significantly, and if we had rounded differently, we may have ended up with a very different answer at the end. So in this case, we could maybe experiment how much variation would happen if we had rounded the value a little bit differently.